we were talking about solubility rules and how we can use them to separate a mixture of, or a potential mixture of some cations. And we had lead 2, ammonium, barium, and copper 2. I was thinking about this, and I don't remember which order we had it. What was the first compound that we added?
It was like a sulfur.
Okay, that won't work. Okay, we had to switch the order. If we add, okay, sodium sulfate, looking at your solubility rules, what would that precipitate out? Right? What else? Remember that list of solubility rules in your book it's hierarchical. So if there's a rule that's higher up with a lower number, it takes precedence over a higher number or one lower down. So that's on page 329. So if we add sodium sulfate, right? Basically, we're adding a sulfate ion. Because sodium, anything's pretty much soluble, right? See rule 3 right there? It says that most silver, lead, and mercury 1 salts are insoluble. That's higher up in the list than the rule for sulfates, which is rule 6, which says that most sulfates are soluble except for calcium and barium. And so what that means is that not only will barium precipitate out with sulfate, but also lead 2 will. Do you see why the rules say that? No? No? Yes?
To be honest.
You're looking? No? The reason is rule 3 comes before rule 6, right? And rule 3 says that most silver, lead, and mercury 1 salts are insoluble. Which means, okay, so lead, that's talking about this right here, combined with sulfate, that would be a lead salt, and that means that it would be insoluble. Which means that it would precipitate out. You guys see what I'm saying there? Rule 6 says that barium sulfate would also precipitate out. When we're doing this sort of separation, we want to avoid that. But we can avoid that if we just change the order. What was the second compound that we wanted to add? So, sodium chloride. What happens if we do that first? Basically, chloride. Looking, and again, you should have those. If you have your book, you should have those solubility rules in front of you, page 329. That's what this is all about. So we're adding chloride, and we have these in there, right? What does it say about chlorides? Soluble, except for what? Look at the rules, right? See rule number 3 comes before rule number 4, right? And rule 3 says what we were just talking about: most lead, silver, and mercury 1 salts are insoluble. So what that means is that lead 2 chloride, it's going to be insoluble. Are you guys understanding that?
We want to do that one first.
We want to do that one first. The reason is barium chloride is going to be soluble. Rule 4 says that chlorides are soluble unless there's a rule higher than it that counters it, right? So barium chloride will be soluble, copper 2 chloride will be soluble, ammonium chloride will be soluble, but lead 2 chloride won't. Do you guys understand that? And so the first thing we want to add is sodium chloride. So what will happen when we add the sodium chloride,
That's not that bad at all.
is it won't interact with the ammonium. That'll still be dissolved. Barium, and then copper 2. But as long as we add enough sodium chloride, all of the lead 2 will precipitate out as lead 2 chloride. You can get a solid form, right? So if we filter it, like you guys have done in the lab, use gravity filtration like with your glass funnel, or if we're in a hurry, I guess use vacuum filtration. Either way, we can filter out the liquid, filtrate. On the filter paper will be the lead 2 chloride. You can set that aside. And then we'll have just these ions in here. Is that making sense? Now what do you think we should add?
Or sulfate.
Yeah, now if we do the sodium sulfate, because we've taken all of the lead out, now the only thing in here that the sulfate will form an insoluble product with is the barium. And so then we'll have, the lead's already gone, so I'm just coming back around to here, okay? Lead's gone. We'll have barium sulfate precipitating out. We filter this. We'll get rid of the barium sulfate, and the filtrate, the solution will have just ammonium and copper 2 in there. Step 2, sodium sulfate. And what now? Carbonate works. Any of those things that are going to precipitate out copper 2. I'm mostly looking at rule number 5 there. Carbonates, chromates, sulfides, oxides, phosphates, any of those, right? So one is sodium carbonate. That's going to precipitate out the copper 2. Again, filter it. So now all we have left is ammonium. And I asked you guys to think about what you might add to that. Because it's the next thing that we're going to talk about. One of the next things. Did anybody figure anything out? I guess not. I'm going to leave that for a second and come back to that in just 1 minute. I'll show you what they did. What's going to help you figure that out is the section where they talk about what are called gas evolution reactions. What that means is, for us, basically you're going to memorize 4 different things. If you ever are forming products in a double displacement reaction and you get carbonic acid, it's not stable. It doesn't exist, as far as we're concerned, in aqueous solution. If you ever get H2CO3 carbonic acid, you just have to remember that it dissociates into water and carbon dioxide gas. So just memorize that. And you have to recognize it though, because what will happen is you'll be doing a double displacement reaction, and you'll get that as one of the products. You just have to recognize that you don't write that down. That's not a product. It breaks apart with water and carbon dioxide. it ends up that these are two really stable molecules. Carbon dioxide has really strong bonds, and water is a very stable molecule too. More stable for these to exist than it is for this. It breaks apart. The other one, another one that you just have to remember, is sulfurous acid. Breaks apart into water and sulfur dioxide gas. Another one, ammonium hydroxide. Ammonium hydroxide will dissociate into water and ammonia gas. And the last one, you just have to remember that hydrogen sulfide is a gas. And if you get hydrogen sulfide as a product, it's going to bubble out. It'll be a gas. Smelling gas. It's a gas. So memorize these. Now, how do you think we can detect whether or not ammonium was in that solution? Not just by itself, right? Because it could have come from ammonium chloride or ammonium nitrate or something, right?
You add like hydroxide?
Add hydroxide, sodium hydroxide. If we add sodium hydroxide, then initially you get ammonium hydroxide, which would dissociate into water and ammonia gas, which you can smell. You know, it smells really bad. You'll be able to smell it. So that's the third step. The fourth step comes in. So originally you had, potentially anyway, ammonium, copper-2, lead-2, or barium, or barium. One or more of those, right? So what you would do is you'd add sodium chloride. If you get a precipitate, one, that means that there was lead-2 ion in there. Filter it, get rid of all the lead. Add sulfate. If you get a precipitate, that means that there was barium, rather, in there. If you get a precipitate, filter it. Add the carbonate. If you get a precipitate, that means that copper-2 is in there. If you get it, filter it. And then finally, after all that's done, add sodium hydroxide. And if you get the ammonia smell coming off, then you know you had ammonium in there. That makes sense?
What's the last one? I didn't catch that.
Down here or
Yeah.
here? This is hydrogen sulfide.
Okay.
And the only thing you have to memorize about it is that if you form that as a product, it's going to be a gas.
Okay.
Not aqueous. It's not
Is that carbonic acid you said? This is bicarbonate?
Is that
Bicarbonate? Is there also?
bicarbonate is HCO3 minus. It's a polyatomic ion with a hydrogen on here. It's not that. If you acidify a solution of bicarbonate, you'll get carbonic acid. That's why when you add vinegar to baking soda, you get the bubbles. Okay. So. next type of reactions that they talk about are acid-base, or also called neutralization reactions. You guys know how to tell if something's an acid from looking at the formula, right? How do you tell? It
Hydrogens.
starts with hydrogen, right? Do you know how to tell something's a base?
OH.
That's, yeah, most of the bases you'll encounter at first are metal hydroxides. There are several definitions actually of acids and bases. The Arrhenius definition of an acid is something that produces hydrogen ion in water. And a base something that produces the hydroxide ion in water. So most metal hydroxides, at least from group 1, group 2 metals, are soluble, which means when you put them into water, they dissociate and produce the hydroxide ion. First, hydrogen in acids dissociates from the rest of the molecule, makes hydrogen ion. We'll save the other definitions of acids and bases for later, because all we really care about are the reactions. The reaction between an acid and a base is just a specific type of double displacement or double replacement reaction. For example, this is nitric acid, potassium hydroxide, that's an acid. This is a base. So to figure out the products, all you really have to do is treat it like any other double displacement reaction. Take this cation and pair it up with this anion. Take this cation, which is the hydrogen ion, pair it up with this anion, hydroxide. What do you get when you combine hydrogen ion with hydroxide?
H2O.
Water. Yeah. So it's going to be potassium nitrate and water as the products. Soluble or insoluble? Soluble, right? Rules 1 and 2 both tell you that that's soluble. And water will be a liquid. And I should be balanced. That's that for now. Next week in lab, we'll be doing acid-base reactions. You're going to make up a solution of base. You're going to standardize it, titrate it. That is, figure out its concentration. And then you're going to use the sodium hydroxide base solution that you made up to figure out what the concentration of an unknown solution of acetic acid is, as well as the molecular weight of an unknown solid acid. That's the next one. The next topic that your book talks about are net ionic equations. This is how you write a complete ionic, a net ionic equation. For example, that equation, that acid-base reaction that I just wrote up. So this would be the molecular equation. When I say molecular equation, I mean just a regular chemical equation. The next step is to dissociate everything that's aqueous. So you have to know the solubilities. Right? If you said that it's aqueous, which means it's soluble, you dissociate it. You write it as its component ions. So what would that be for nitric acid? What would its component ions be?
H plus and 3 minus.
What's that?
H
Hydrogen ion. And
nitrate ion.
potassium hydroxide.
Potassium.
Potassium hydroxide. Potassium nitrate. There's potassium. Water's not aqueous, so you leave it as is. So if it's not aqueous, if it's not dissolved, that means it's solid, liquid, or a gas, just leave it. What we have here is called the complete ionic equation. To get the net ionic equation, just cancel everything that's identical on both sides. So nitrate's identical, and potassium is. What's left is the net ionic equation. What's nice about a net ionic equation is it focuses on the actual chemistry that's happening. The species that you canceled out in this step are called spectator ions. Because they're only there to balance the charge of the other ions. Only, nitrate balances the positive charge of nitric acid and so on. But they don't do anything. So the real chemistry that's happening in this equation here is that a hydrogen ion is reacting with a hydroxide ion to make water. That's it. The next type of reaction that your book talks about is an oxidation-reduction or redox reaction. So first of all, what oxidation means is that it means loss of electrons. Reduction means gain of electrons. When something loses electrons, we say it's oxidized. When something gains electrons, we say it's reduced. There's a mnemonic. Helps. Oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. An example. This. And the way that you can tell at this point, okay, we're not the third. There's a method called oxidation numbers. You'll get to that in Chem 102. For now, the way that you can tell that an oxidation or a redox reaction is occurring is that the charges on the ions will be changing. And it's particularly helpful to look at the net ionic equation to see this. So let's write the net ionic equation. Remember, we're going to write the complete ionic equation by dissociating all the aqueous species and then canceling with the identical species. So this is solid, we leave it as is. This is aqueous. What's the charge on copper here? 2. 2, right? Copper 2, because each nitrate has a -1. This is aqueous. That 2 shouldn't have been there, should it? that okay to get you guys see that that's what the complete ionic equation is? So what do we cancel? Right, we want to get the net ion.
The
Nitrate
nitrates.
cancels. Anything else? No, right? So we have the net ionic equation. Now we can see the real chemistry that's going on. We're taking metallic magnesium with no charge on it, and a copper 2 ion, and we're making magnesium ion and copper metal with no charge. What has to be happening? How can you go from no charge to a positive 2 charge?
2 electrons.
You have to lose 2 electrons. That's the only way that that can happen. So you can see that magnesium had to lose 2 electrons. Where do you think they went?
Copper.
On a copper, because the copper has a positive 2 charge here and a 0 charge over there. The only way that can happen is if it gains 2 electrons, right? So the charge is changing, electrons are being transferred. This is a redox or an oxidation-reduction reaction. And we can say a few more things about it. Remembering that oxidation is loss of electrons, which species is being oxidized here?
Magnesium.
Magnesium is being oxidized because it's the one losing the electrons. So what must be reduced?
Copper.
Copper, because it's the one gaining electrons. Reduction is gain of electrons. Okay, so far? One more slight twist to this. Some terminology that's commonly used is oxidizing agents and reducing agents. Now, I'll write it down in a second, but listen for a second. You've got to get it. An oxidizing agent is what causes something else to be oxidized, which means that it itself is reduced. So whatever is being reduced is the oxidizing agent. A reducing agent is something that causes something else to be reduced. The only way that can happen is if it itself is oxidized. So whatever is oxidized is the reducing agent. I'm going to write all that down in a second, but think about it. Okay. So if you put the word agent at the end, that means it's the opposite, right? The oxidizing agent is something that causes something else to be oxidized. And the only way that can happen is if it itself is reduced. The reducing agent causes something else to be reduced. The only way that can happen is if it itself is oxidized. Okay, let me write that down. That. So in our example over here, what's the oxidizing agent?
Copper.
Copper, right? And so that means that the reducing agent is and magnesium, right? Whenever you see something reacting with oxygen, O2, it's most likely going to be a redox reaction also, for combustion reactions, right? Remember combustion reactions? No? Yes?
That's oxygen and carbon dioxide.
That's right.
Okay.
So combustion means reacts with O2. If a hydrocarbon is being combusted, if it's a hydrocarbon, and what that means is a compound that contains carbon, hydrogen, there might be oxygen in there too.